Right, the queue. The second of the fundamental data structures. We looked at the stack last time. The stack is used for organising interrupts, calling functions, remembering things, and you use it in backtracking. When we do recursion, we use the stack. Okay? The queue is the other fundamental one. We use it all over. So when you've looked at scheduling, did you look at that at GCSE?
No.
Multitasking?
Well,
You've got a vague idea about multitasking.
The basics.
Oh yeah, the basics.
Yeah,
Not like
multitasking.
threading or anything like that.
No. But
Just common sense.
But we use queues in order to manage the processes that we want to multitask, that we want to switch between. Okay, you don't just like randomly store them somewhere, you store references to them using queues. The queue works identical to a human queue. Okay, so if you ever get completely lost in an exam, just think, right, last time I was stood in the queue, how did it work? And obviously don't like start saying, oh yeah, well people pushed in and stuff, and they pretended they knew someone at the front and they went, oh, and then pushed in, like people do, but it's not like that. Obviously you could implement a queue like that. It would probably not work very well. So it is a fundamental structure. It is there to store things and remember things in the order that they arrived. That's different to the stack. Remember? The stack remembered the last thing. It was in order of the last thing that arrived. This will allow us to hold things temporarily before we can process them. So we process them in the order that they came. Just like a human queue. We can implement it using lots of different data structures, but we usually think about queues as arrays again. But you could implement them using lists. And when we look at linked lists, you'll be able to see how that's probably actually quite advantageous. Okay. But in general, we'll use an array. So we've got an array structure. Again, if I was to give you this array, what could you tell me about this array?
Length of 8.
Yeah, length of 8. So elements not 7. Obviously, that is a significant thing because just like the stack, we've got a finite amount of queue space. Okay, we can't actually just keep adding on extra space. So because it's an array, it's static, and we have to decide how big a queue do we need when we declare the array. But it is another example of a dynamic structure. It's going to change size as we add things and remove things. Okay, so we call this a FIFO structure. First in, first out. Okay, so whoever arrives first, we're at the front of the queue. When you arrive to join the queue, you join at the end. Two stupid names for these. Adding something to a queue is called onQueue, not add. I don't know what the implications are with the example. If you was to put add, if you were asked to write a algorithm for adding something to a queue and you called it add, I don't know how picky they'd be, but just try and it's on queue.
Why is it on queue?
Don't know.
You add it on queue.
Don't know. It's an odd thing.
Is it French?
I don't know. Don't know. No. Don't know. Right. Removing something from the queue is not removing, it's dequeue. Queue is a horrible word. Too many U's and E's. It's like, it's way around it all. Right, so the process of adding something to the queue is called onQueue. The process of removing it is dequeue. Okay. Now, the stack, one of the things that's really nice about the stack is it uses just one pointer. That's all we have to manipulate. But with the queue, we need 2 pointers. One to say where the front of the queue is, and one to say where the end of the queue is. So, loads of different names you can call these. If you're doing an algorithm, pick a sensible name that would differentiate between the front and the end. Okay, don't just say A and B or something like that. So, yeah, you can have front and back, front and end. Don't know what else you could put actually. So we have front. Now, in a traditional queue, what we can do is we can add members to the queue, and we add to the end of it. So in this example, at the minute, the front and end pointers, because it's empty, the front and end pointers both point to the same location. So if I want to unqueue something, so again, what I did with the start, I'll just use numbers again. Remember, these numbers potentially are keys that refer to particular records of data, or there may be a memory reference. So it's like, oh, there's something in memory that we want to process. So it could be like, if it was multitasking and it was a queue for the scheduler, which you will do, you need to know about that. So the scheduler will keep process IDs, PIDs. And that's, you know when you're like, you bring up task manager and you start playing, anyone played the random process kill game? Have you never done that on a computer? Make sure you...
Can't do it on these.
Yeah, no, you can't. Yeah, bring up task manager, make sure you say show all processors, so you get the system ones as well. And then just, in process, we right click and say end process, see what happens. See how many you can get before the computer like upends.
I like hacking.
Well, I have done it ended this PC.
Hack the network.
It's funny when you,
Rise up.
if something goes wrong with a Chrome tab, and then you go and say, oh, I'll just kill that tab, or something like that, and you're like, you see there's like 30 Chrome instances in the process list, and you're like, oh God, which one is it? And it's like, oh, I got the wrong one, and the whole of Chrome's gone. The master one's gone. But yeah, that's quite a good game. I like quite doing that. Okay. Anyway, right, so if we add something, so these numbers would refer to whatever it is we're holding in the queue. So let's say I add 76. So I look where the end pointer is, and I say, okay, the end point is pointing, and now this is really important when you're reading a question, they'll describe how the end pointer works, whether it's pointing at the free space, or whether it's pointing at the last item. So you'll need to look, they'll probably give you a diagram, and you'll see this when we look at a few exam questions. They'll give you a diagram. You've got to read the diagram carefully because it will slightly alter if you have to write an algorithm. All right, be careful of that. There was one question where they put the front at this end and the end that way, and they made it go that. I don't know why they did that. It was very confusing. But you could work it out from the diagram they gave you. So I'm going to add 76 to the queue. So in my instance, I'm just going to say the end point. No, don't do that. The end pointer is always pointing at a free space. So end is now, I'm just going to put E, because I can't bother trying end. So end is there. If I add something else to the queue, it goes on the end. So let's say I add another number. So my end, I'm not even going to put the arrow. Let's get rid of that. I'll try and make it easy for myself. Okay, if I want to remove something, so if I want to dequeue, I only look at the front pointer. So we have got two pointers, but actually the two separate processors, onqueue and dequeue, only are concerned with one of the pointers. So again, the code when we come to write it is actually quite simple. Simple error checking to make sure that we're not empty or full and things like that. And then simple manipulation of a pointer. Okay, so if I try and remove something, I can't access the 54 because that's not at the front. So the thing that gets processed is the 76. So the 76 comes out, and as usual with everything we do when we're programming, we do not delete the 76. It just sits there, ready to be overwritten. So to remove it, all we're going to do is we're going to put the front pointer there. So it moves. So we grab the data and then we move the front pointer. Okay? Any questions so far? Queues are simple. Okay? Right. We keep doing this process, adding things or on-queuing things. My brain finds it really hard to think of numbers. Right. At this point, the queue is now full. Even though the front point is there, we can't access that location. So we've run to the end, we've filled the queue up. In this format, these queues are effectively acting as a buffer. That's what a queue is, it's a buffer. You've heard the word buffer, we use it all the time in computing.
Don't know what it means though.
Don't know what it means. It's just a temporary area of memory where we hold data that we're waiting to process. Okay, and a buffer generally holds the data in a queue format, in the order that it arrived. That's not always strictly true. When you're video streaming and you're buffering, what you will actually do as packets of data arrive, you did packet switching, didn't you?
Yeah.
So you know that packets make their own way to their destination, so there is no way of guaranteeing what order they arrive. So they're all numbered. And what you would do is you would have a buffer and you would go, oh right, packet 5's here, wait, put it in there, oh packet 10, put it over there, and so on until, and actually if you want a really good demonstration of this, if you've ever torrented anything and you watch, a torrent is a valid thing actually, it's not just an illegal thing, it's actually a really good way of making use of the internet and the way that packets are delivered. And to reduce load on one server. There are lots of applications where torrents are used, okay, to alleviate load. Although if you just download a file, if you like FTP from a server, that server's working with you, passing packets continually to you. If you could spread that across a load of different servers, then you're going to make better use of your network. It's about network utilization and not clogging up one server so it can respond to requests. So if you ever do that when you're torrenting something, if you look at, you can usually look at the little packet graph and you'll see them getting filled in, and they're getting filled in all over the shop. Depends what, if you're using the normal BitTorrent client, it has the little graph at the bottom and you can see, oh, that packet's arrived, that one, and it fills them in. But that's basically buffering. Basically just one massive fat buffer that is recording what packets have turned up and what are still left to come. But anyway, right, so a queue is a good way of implementing a buffer. Okay, so a temporary area in memory for holding data before we're ready to process it. So now that we've filled it, we can't actually add anything else until we empty the queue. So we'd have to dequeue everything. So eventually, let's just rub all this out. So the end pointer is there. If we dequeue, we'd get that value, then we get the 36, then we get the 41, then we get the 30, then we get, and we just move it. Notice the way the pointer's moving. Which direction are they going?
Right.
They're always going right. So all we're going to do is increment. So to adjust these pointers, we're just saying add one. Quickest instruction at CPU level is to increment. Okay? So operating these is monstrously quick. So we keep going. If the front pointer is there, we are down to our last item. Once we remove that, the front pointer goes there. So what is the condition that tells us that we've exhausted the queue?
The front index is equal to the length.
If the front pointer has got to 8 in this case, then that queue has been completely emptied. At that point, we can reset the 2 pointers, put them back over here, and say, you know what, yeah, there's a load of data in there, but I'm telling you the queue's empty. You do what?
Get that.
You're in the wrong class, mate. Luckily you didn't come over here and stand in front of the camera there. But I've got it all on tape, you'll be able to watch it later. This is what production values are. Top of the range. Right, so once we've got to that exhausted situation, so we've got two situations. We've got, we can't put anything more, so if the end pointer ends up equaling the length of the queue, then we've filled the queue. We can't add any more values. If the front pointer ends up over there, then we have emptied the entire queue and we can reset and fill it again. Okay? In general, when that occurs, you can get issues. So there is something called a double buffer. So that once you've filled a queue and you've still got more data that you want to put in the queue, what you do is you have a secondary queue and you start filling that one. Okay, this is what graphics cards do. They double buffer. So when you're showing a scene on the monitor, you're actually creating the next scene in the background. As soon as that scene is ready and it's finished being rendered, you flip and you get the graphics card to draw on the screen the one that you've just done, which means that the old one, the old buffer, is ready to be filled again. Okay, it's a process called double buffering. I don't think it's on the spec anymore, but it's important to know about it. And by doing off-screen rendering, you can stop getting screen tear.
Oh, that's what meant to do this.
That is what screen tear is. Screen tear is where you've got one buffer. So you're displaying it on screen, and you didn't finish building it again before it started to be displayed again. So you've got the new stuff and the old stuff. And depending on how much movement there was between one frame and the next, decides whether you actually see it. If you swung your arm in an FPS game, or your mouse, not your arm, unless you're doing some sort of VR rubbish. If you swung your mouse when you're doing that, and you moved, let's say you moved 30 degrees, you are going to get screen tear with a 30-degree difference, which can be quite jarring. That is why in VR games you have got to make sure that you complete your rendering before the frame's going to get redrawn. Because if you do that in a headset, your brain is incapable of saying, right, the top half of the image is where I am looking now, the bottom half of the image is where I was looking 60th of a second ago. Your brain won't cope with that and you will throw up. Because you're breaking an illusion. Your eyes are making a contract with your brain to say this is what your reality is. If anything stops that being true, then your brain goes, there's something not right here. I think my natural reaction will be to throw up. And I've never understood why that's the natural reaction of the brain. To say, I'm a bit confused here. I think the best course of action is to throw up. Contract the stomach muscle, get them to contract.
I think it's just, I think you've been poisoned or something.
It is a weird thing. It is a weird. I don't understand why that happens. Obviously, that doesn't happen to everybody. Some people can deal with that. But I know when I played Drive Club VR on the PS4, and amazing. You're sat in an aerial atom, and you load it. I was laid on the floor, sat on the floor, so it felt really real. Yeah, so you're in a really low racing car, so you sat on the phone and think, yeah, this is really good. You're looking around and think, yeah, it's amazing. I mean, you accelerate and think, it's alright, I'm alright. And then the first track on Drive Club VR goes slightly up an hill. I think it's Brands App, so it goes slightly up an hill to the bend, and then it goes woof like that. And that was it. Exit off, quick, oh, I'm sweating a bit here, sweating. 7 seconds I played that game for, before it went back in its box. Slightly off point. Okay. Right, the queue. Yeah, no, it normally is. Right, so it's quite a basic operation. So what we need to focus on is when we're adding stuff, we only are concerned with the end pointer. When we're removing stuff, we're only concerned with the front pointer. Okay? So let's just have a look at what the logic of that is. So let's talk about adding first. So let me just set this up so we've got some known state. Right, I'm going to assume that the end pointer, and like I say, you have to follow the question when you get these, the end pointer is pointing to the free space. Okay, so if I want to do on cue as a function, I'm just doing this in pseudocode. What parameter do I need to give it?
The thing you're going to
add. Does that seem reasonable? The item we want to add to the queue, which we just call item. Just keep it simple. Yeah. So I'm going to pass to the on queue code. I'm going to say, this is what I want to add. I don't care how the queue works Just want to use it. But obviously I'm writing the Q code here, so I do have to worry about it. Right, so the first thing we need to check is what? Think back what we have to do with the stack.
So it's not full.
Yeah, does that seem reasonable? Not full. Check. So what did we say was our condition for not being full?
When it's the end is 8, the length.
If the index is
array.length.
Right. There's loads of ways of doing it, but what's the right? Standard thing
E does not equal length.
is to use KISS all the time. Keep it simple, stupid. Okay? That's super important. You can make this as complicated as you want, but at the end of the day, you're aiming this at an examiner, and you're hoping that that examiner knows more than what the mark scheme answer is going to have. Okay? But you can't guarantee that, which is always a concern with this subject. We're talking about a super technical subject where there is no one way of doing anything, and there's probably 1,000 ways of writing on Q, if you really wanted to. So we've got to keep it simple. So we're going to do a test. So we're definitely going to say something about E. Right, so in this example, 3 is going to be okay. So if E is 3, it's going to be okay, isn't it? So that's all right. If E is there, so always give yourself an example. If E is there, we're still okay.
E is less than the length.
So yeah, if E is there, so that would be the magical 8, that's no good. So as long as we're less than the length, that should be okay, shouldn't it? So our test, so okay, as long as we are less than, I'll call it Q because I'm being lazy. Whatever remember you can do it a couple of different ways. They'll accept that as pseudocode, or you could do it as len Q, whichever. Just be consistent. Don't keep randomly changing things. Right. So as long as that's the case, then we're good to put something in. So in our example here, end is marking the free space, just like we did with the stack and the stack pointer. It makes sense to use that same structure. So I can say Q at position E, set that to my item. What do I need to then do with E?
Increment it.
Increment it. Yeah? E++ or do that just to make it super clear to someone who only knows Python. Because there is no E++ in Python.
You wouldn't like Mr. Green.
Could you do E plus like equals 1?
Yeah, you could do that. That's Python. In most languages let you do that. Visual Basic doesn't. So, again, just make it. Do you know what my main thing is? If there's any code in the paper that you're doing, and they've used a particular way of writing something, and you can see something like this, copy them. Just say, oh, you know what, I'll do it in your format then, fine. If they give you some code to fix, stay with their format, in general. Right, okay, is there anything else we need to do? So we've added it, we've done the increment.
Oh, really? Okay.
No.
Right, the only other thing is to do the error.
Oh. Throw exception.
That's a very weird E.
That's a weird S.
Yeah, it's not a mix of joined and...
Yeah, no, my brain doesn't work very well. If anyone tried to analyse my handwriting, they would be quite shocked. They'd probably say I was a psychopath or something. There's nothing consistent about anything I write. You can see I've got like mixes of cat, lowercase, all over the shop. It's my programming style. No style. Right, that is on Q. Again, it's doing what a function should do, one job. It doesn't care how the error is going to be handled. We don't care about that. That's for the person who used the onQ function. We don't care what's happening with the front. We don't do any checking at the end to see if it's full because we've set it up that way. The entrance to the function is guarded by the check to make sure we don't try and add something to a full Q. That is it. DQ is the same, but we're messing about with the front pointer. So I'll give you a couple of minutes. I don't think I can pause this, so I'll just wait on the video and just talk or something. Try and write the DQ. So same structure. Yeah, the one to remove. So it needs to return an item. So remember, in this case, the front pointer points to the first item in the queue. So we're already at the first item. So F in this case. No parameters needed because obviously it's just going to give us what's at the front of the queue. What's the matter?
It's not letting me create a class called Q.
No, just do it on paper.
It's just for when I do it.
What's it say?
Add class.
Ow. Where's the queue?
Thank you.
Have you got any? Where have you got this saved? Have you copied it or are you trying to edit it in? You've not got no right hand to that folder.
Just do it on paper. You're going to have to get used to it. In the exam, they're not going to ask you for actual language code. They're just going to ask you for pseudocode. Because they can't dictate what language you study. And the language is irrelevant. It's the algorithmic structure that's important. The selection, the looping. That's all they're interested in, really. Don't get bogged down in implementation details, just we're keeping this basic. No, because implementation details fog the algorithm, because it depends on the language. So we need to just nail the pseudocode down for this. You've got 15 minutes, gents. Make sure you check your answers. No, not you lot. No, the people at the back of the room doing their test. Right, okay, let's have a look at this together then. Right, so I've got that example, but I'm going to give you another example in a minute. Right, so DQ. We need to make sure that we have got a queue with something in it. What test are we going to have?
One that is greater than,
If f is greater than q double.
greater than or equal to 0.
Or 0.
No, because it's the front pointer.
It's greater
Oh,
than or
yeah.
equal to 0.
Oh.
Oh, that's,
Wait.
that means it.
It's always going to be greater than or equal to 0, isn't it?
Yeah.
Because you don't have negative indexes.
True, but I thought you were asking. That's checking if it's full. If it's that
No, it's
full.
not. What? It's checking if it's empty.
Oh, because it's f not e.
If it's
Yeah.
empty space.
Yeah, it's the other point.
Oh.
Right. This isn't right, but let's just run with it.
Oh.
Did that in
Right. If we are okay to read something from it, which is what we're checking for here, then we need to return an item. This is a function. It's going to return an item. So we might do this. So return whatever is at the front pointer. Yeah? Does that seem reasonable? And then we need to increase the front pointer and move it along, don't we? So if I've read that value, I need to say, oh yeah, let's move F on. So it points to the new front. Because we've taken something from the front. Yeah? So I'll do this. Else error. Q empty. There are a couple of problems with it. Anyone spot them? Go on.
When it says it's smaller than length, if it's at 0, then it will still be empty, but it won't think it's empty.
What would the setup be to show that?
Well, if you haven't enqueued anything yet, so the F and E are both at 0.
Right, yeah, right, okay. So if I've got them there, so there's some junk in there, but if I've got them there, you're saying that's empty.
Which still thinks it's empty. Well, if you're putting E to be the empty.
Yeah, yeah. If I'm saying, yeah. So how can we generalise that then? So do we actually need to worry about the length?
No.
As long as it's less than E.
Yeah.
That's the key. As long as the front pointer is not at the same position as E, in this way that we're using E. So it doesn't matter whether E's there.
That's not E.
If E's there and F's there, then there's something in the queue, isn't there? Because E's the end, where the next space is going to be. So in that example that we just had, and the only way, if you don't really get it, give yourself examples, and you say like, okay, yeah, there's something in the queue. F is less than E, isn't it? If I remove everything, I'm going to rub them out so they're not there. But if I remove two things from the queue, so dequeue two things, I've got one thing in there. F is still less than E. If I remove that one, they are the same. So I can write this a couple of different ways. I can say, if they're equal in this setup, where the empty part is where end's pointing, if they're the same, then the queue's empty. Can't I?
Yeah.
Or I can reword the logic and say, like Callum said, if F is less than E, then there must be something in there. Does that seem reasonable?
Yeah.
So actually, the length in this case for the front pointer is irrelevant.
If F
Yeah? Because if we're in that state, we know we can't remove anything. So we're not going to accidentally try and remove something that isn't there. Right, that's mistake number one fixed. So we're checking for the status of the queue correct. So that's okay. What other mistake is there? A fundamental mistake. Which is the only thing that complicates this a little bit.
Is it the return?
If it's
Go on, Callum.
Is it because the return is before you're incrementing the A?
Yeah. If you put that in code, look at this. Return. What does return mean in a function?
stop it.
Stop processing the function and pass a value back. Which means this line of code will never execute. And in fact, if you put this into a decent compiler, you'll get a squiggle and it'll say unreachable code. Unreachable code, which means, yeah, fine, you've followed the syntax of the language, it's correct, but this is semantically wrong, i.e. it's not what you intended. What you intended to do was to return the value, but do the increment as well, but afterwards. So what can we do to fix it? Without going all how real programmers do it. I'll show you how real programmers do it in a minute. Go on, Callum, you're on fire.
Do you do the increment first and then return F minus 1?
You could do it that way, but that starts getting a bit bodgy. Right, this is a standard thing that you may come across, where you want to grab a value, alter a pointer, but you want to return that value. So,
Temp.
yeah, do a temporary. I'm not going to call it temp though, because I'm going to call it item. So I'm going to grab hold and store the item that is at the front of the queue. Then I'm going to increment the queue. Once I've done that, I can then say, oh, okay, return the item that we temporarily held. Like I say, there are millions of ways of writing this 5-line program. It doesn't need to get any more complicated than that. A real programmer would do it like this, in a real language. I do it in one line, because that's what you do. So that was the preferred way of writing it. This is the programmer's way of writing it.
Oh, this is the thing on that program, code balls.
Okay? You make use of what we call post-increment. So we process this line. So as this expression is evaluated, we go, okay, what is the value of f? Look it up. Going to return that value. But when we've finished executing this line, increment f. So it works. But the preferred one is the one I had prior to that. So temporarily grab hold of the item, increment your pointer, return your item. Okay? Now, if you was trying to do this as is, but again, the compiler will say not all paths return a value because they're not returning. But the way that we'll do this in our code is we'll throw an exception here which terminates the function anyway and passes control back to whoever called it if they bothered to handle the errors that they could get using the try and catch. If they didn't, then the runtime that the compiler's built for us will throw the exception to the user, which we tend to not want to do. That's what happens when you get an error in a game and you get like a massive hexadecimal code comes up with some random numbered error message, especially on the PlayStation when it goes, oh, error CR36492.
Wait, so what does that mean?
What?
You know what that means?
Oh, yeah.
No, it just means, there's a fatal error that hasn't been tracked by the program. So when the programmers don't know about this book, basically, is what it means.
So stupid.
And it is of no use to the end user whatsoever. Basically, if you've got bugs that throw exceptions that you don't handle, then you're giving your user a really poor experience. And probably in any other industry, this would cause you to lose sales. But in software, it doesn't seem to matter. Software is complicated. And I think most people don't understand because they've never tried, don't understand how complex writing anything is. So there's always going to be mistakes. I think someone worked out that the biggest program you could write that didn't have an error in it was about 8 lines. Anything above that, you are going to make mistakes. Maybe because you've made a mistake or you don't understand the problem enough, which is what happens a lot. Say that's onQ and that's DQ. They are the two processes. So it's the equivalent of push and pop on a stack. Okay? So that is a standard queue. So we fill it, we empty it. But there is another type of queue called a circular queue. Now I'm not going to go into the detail of this, but I'm going to show you how it works. Right, a circular queue. I'm videoing it, but you should have been writing it down when it was up there. Right, so let me just set up a state of a queue. Okay, same process, onQ and DQ, but this is now going to be a circular queue, so I'll just write the word circular there. Like magic. Right, add things to the end. So the end pointer again, I'm using the end as pointing to the next space. So add a new item. Increment the end pointer. If I add a new item, in our previous version, the end pointer would end up there. But in a circular queue, what we say is, hang on a minute, we've got some space, let's move it to the front. So if we go off the end of the array, we go, you know what, let's put the end there. When I add my next item, it goes there. Slightly more complicated to manage the status of the queue, whether it's full or not. Because Callum's brilliant system for determining whether the queue had some content is broken, isn't it?
Sorry.
Alright, so F is no longer less than E, even though there's stuff in the queue. So what you have to do, you keep track of how many things are in the queue. So every time you on-queue, you say count +1. Every time you dequeue, count -1. And just check that, see if it's 0 or equal to the maximum. Okay? I'll leave that up as an exercise for you to try and implement. Okay, but that's a circular queue. It's not mentioned in the spec. It used to be part of the syllabus on the old computing course. But it's a bit more efficient. You can keep going. So the only time you can't add something is if the queue's full. As soon as one item's removed, you can add a new thing again. So it's a bit more efficient than the other queue system. Okay, that's circular queues. I'll upload that